Welcome to another RDWorks Learning Lab. Today we're going to carry on with our hunt for the 1000 DPI dot. Now, I've got this feeling it's a bit like chasing the pot of gold that's at the end of the rainbow. A couple of years ago when I was in Ireland, I did actually see the end of the rainbow right in front of my car as it was parked in a lay-by. So I know that there is no pot of gold at the end of the rainbow. Except when I got back to my host, he said to me, "Oh, to be sure," he said, "you were looking on the wrong end." Now, in the last session, we were using these lens tubes, and we started off life with a lens at the top of the tube here, a 4-inch lens, which was focusing down onto a lens that was positioned just here with my specially manufactured lens holder that allowed me to put a lens just here. And that in turn allowed me ultimately to use a shorter 2.5-inch lens and a 2-inch lens, so that I had a compound lens system that I was working with. That has produced some very interesting and quite good results. When I did the video editing for the last session, I realised that I had been tempted by all this gold at the end of the rainbow. I had been blindly changing lenses and getting results, and changing lenses again and getting better results, and changing lenses again and getting better results. Now, there was no logic to what I was doing. I was just following my nose. Now, that's a bad thing to do, because you don't know what you're actually doing. You're getting results, but without any logical explanation. So it was when I was doing the video editing, I thought to myself, I recognise a pattern here. So I went back and looked at something I asked you to read carefully, which was this document from Parallax Technologies, Inc. Now, as it says here, to reduce the spherical aberration, we want the smallest beam diameter and the longest focal length. Now, that's where we started off, if you remember, with a 4-inch focal length lens, which was reducing the beam diameter down to a very small beam, 3mm diameter, before it hit the second lens. So effectively what we'd done, we'd produced the smallest beam diameter, and we had got the longest focal length, which I'm not so sure that we did because we were using fairly short focal lengths, to produce the second focused beam out of the second lens. That was the basic principle upon which I was working. But then, as I was looking through my editing results, I realised that what had happened was, as I was gradually getting improved results, the distance between the front lens and the back lens was getting shorter and shorter, and I was using a shorter focal length lens as well. So the net result was exactly the opposite of what we'd got here. We'd got a larger beam and a shorter focal length. Well, let's just look at the statement below, which basically says to minimise spot size that comes about from laser properties, we wanted the largest beam diameter and the shortest focal length. That's what I missed by chasing that pot of gold at the end of the rainbow. I stopped thinking. And so today what we're going to do is we're going to approach this problem in a slightly more logical fashion. Now, as I've mentioned to you before, I have a little knowledge about a lot of things. And sometimes that's useful, sometimes it's very annoying. Today, I'm going to dig back way into my past, and I'm going to show you a magic trick that the light plays with you and your eyes. Now, here I've got a straight rod, and here I've got a little bucket of water. And as I dip this straight rod into the bucket of water, hey look, it bends. But as I take it out, it's not bent. Now, this is a phenomenon called refraction. Basically, the difference between the light conductivity through water is different to the light conductivity through air. And that causes this apparent bending of the rod. This refraction process is exactly the same process that happens when you fire a beam of light at a lens. As you move from one medium, air, to a denser medium, the glass of the lens, the beam changes its direction. And as it comes out the other lens from the dense glass medium into air, it changes direction again. And that is how you steer a beam through a lens. Now, that's about as much as I know about refraction, except that there was a very clever guy called Snell who researched this subject and put it all down as a law. So what we need to do is go and look at Snell's law of how we calculate the amount of refraction that occurs as we pass through different materials. And we're actually going to try and design a lens system. Now, I've never attempted to do this before in my life, but due to the wonder of the big wide world web, somebody else has done it for me. So I haven't got to get my sine tables out and spend hours and hours doing calculations. This is very repetitive, and I should be doing quite a lot of this over the next few hours. Here we've got an angle of a beam hitting the surface of the water. Now, air has got a refractive index of 1. Okay, and now we go into the water, and let's just guess. The water, a refractive index of 2. And there we go, look, we've got a bent rod. So that's going into one side of the lens. Now, coming out the other side of the lens, we've got the opposite situation. We've got a refractive index of 2 because we're already in the water. And we've got an angle of 9.8. And we're coming out into air, which has got a refractive index of 1. And hey, look, it bends the other way now. So this is going to make my life very, very easy. Okay, so where do we start? Well, I know all the dimensions of my lens. I'm going to be using a 1.5 inch plano convex lens, which I can measure. And I can put those dimensions into my CAD system. Then I can take some single rays coming from the laser, and I can plot their path through the various lenses and lens configurations that I'm going to be testing. Well, here's the principle that I'm trying to use. The orange is my lens, which I've obviously measured, and it's a simple plano convex lens. The red lines here are the beams coming from the laser. Now, this two outer lines here represent rays at about 10 millimeters diameter, whereas the inner ones are at about 5 millimeters diameter. Now, I'm not going to do a lot. All I'm going to do is just take these two beams as a sample. And the most important thing is, as this beam enters the surface of the lens here, it is not what they call normal to the surface of the lens. The lens has got a radius on it, and that's what these green lines are. The green lines represent, that's the center point of the curve of the radius. It's a spherical surface, but when we look at it in cross section, it's a simple radius. Now, these lines project out, and where these lines cut this surface here, they are at 90 degrees to the surface itself. So what we have to do is to measure the incident angle of the ray hitting the surface. And one of the things that I hope you can begin to see here is that the ray hitting the surface at 10 millimeters hits the surface at a different angle to the ray hitting the surface at 5 millimeters diameter. And so consequently, these two rays take up completely different positions when they reflect through the lens itself. The beam comes in at one angle to this normal, and it gets into the material and changes its direction. It bends just like that rod. And the closer we get to center, the less it bends. Here we've got our red line, our beam coming in at an angle of 3.2 degrees. Say this green line here is 90 degrees to this back surface, the flat surface of the lens. When this beam hits the second surface of the lens and comes back into air, it changes direction quite significantly, as you can see. It has changed by 7.8 degrees away from the normal, so it's almost doubled its angle of bending. And that's basically what we've got shown here. These two angles operating against Snell's law give us the way in which a lens works. Now, to calculate my angles,
I need to put a refractive index into Snell's law. But the problem is that this refractive index changes for different wavelengths of light. So down here in the visible spectrum, we've got some interesting numbers. Every single wavelength of light refracts in a different way. Now you'll probably be familiar with this anyway if I show you this picture. And if we take a piece of white light and look at the way it hits the surface, violet light has got a very large refractive index. So consequently, look at the bending that takes place on this mauve light. Okay, so it passes through the prism at one angle, and then it passes back into the outside world at almost the same angle. Whereas in fact, if we look at the other end of the spectrum, the red light comes in with very little bending, but it goes out with a lot of bending. And it's that difference between the wavelengths of light that allows you to create this rainbow spectrum. Each colour refracts inside the glass by a different amount. We haven't got to worry about multiple colours. We've only got one single wavelength of light that we're firing at our lens, and that happens to be about 10.6, as I'm showing you here. 10.7, that's near enough, but it's showing a refractive index of 2.4. Now when I use 2.4 in my Snell's calculation, I actually get rubbish results. I know that my lens is a 1.5 inch focal length lens, but if I use 2.4 as my refractive index in the calculations, I finish up with a lens which says it's nearly 50 or 60 millimeters focal length. Total rubbish. Now, I know the lens is 38.1, therefore what I have to do is find a refractive index which produces a result of 38.1. I can't say what quality we've got in our zinc selenide. There is a whole range of zinc selenide qualities that perform differently. This is probably industrial grade zinc selenide that we're looking at here for its refractive index, good quality stuff. The stuff that we're getting from China may well be of a different nature. And all I can do is use the figures that produce the facts. The fact is I've got to finish up with a 38.1 focal length lens. We finally finished up with a refractive index of 2.7, and it produces an end result of approximately this 38.1, which is the correct focal length of the lens. Now because this is a plano convex lens, we're not expecting it to be absolutely perfect with its focal point. There is a certain amount of fuzziness at this focal point. So here we can see the way in which these two rays don't actually meet. One falls short and one exceeds the theoretical focal point of the lens. That gave me a starting point for looking at how I combine lenses together. Now I did some stuff with meniscus lenses as well, as you can see here, but it would appear that my meniscus lens that I have is yet a different refractive index, because the number that works for my plano convex lens, when I put it into the formula and do the calculations for this 2.5 inch focal length meniscus lens, the results are rubbish again. So this is yet again another refractive index that I would have to calculate. Without boring you with all the hours that I spent calculating, trying, drawing, moving, shifting stuff around, here's a summary of the end result that I think we're going to have to examine. I have got two 1.5 inch plano convex lenses shown on this drawing. Up until today, I thought that the right thing to do would be to position them a long way apart. This is approximately the relativity of two lenses that I would have if I could put a 1.5 inch lens into my lens tube and 1.5 inch lens into my special nozzle. They would be approximately 13 millimeters apart. Now, using my 10mm beam, we can clearly see here the way in which the first lens focuses down, we need a large diameter beam into the second lens. Well, yeah, we've decreased it from probably 10 millimeters to maybe 6 millimeters diameter. And look what's happened to the focal length of this second lens. It's come right down to 8 millimeters. So when I push the lenses together with roughly a 1.5 millimeter gap between them, look, the focal length has now doubled. I don't have a 1.5 inch lens 20 millimeters diameter, so I can't mount a 1.5 inch lens in my lens tube. So that's problem number one. I can't actually get them 13 millimeters apart. I could get them 1.5 millimeters apart by mounting both lenses in the nozzle itself. The problem with the 13 mm option is that this focal length here is so short that to get me 5 millimeter gap underneath the nozzle, a reasonable working distance, the lens is going to sit this close. Can you see that mauve line? That lens is going to sit that close to the end of the nozzle. So it's going to be a very, 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 almost a flat-ended nozzle, which I have to say is more or less what you find with the Thunder Laser nozzle. I'm going to be more practical about it, and I'm going to say, well, if I use the 15 millimeter combination, that gives me the opportunity to have at least 5 millimeters below the nozzle. And if we look beyond my arrow that I've got here, I've got a substantial amount of material back that I can use to taper the nozzle down so that you can see what's happening at the point of working. This one says 0.9 spread of the focus point. This one says 0.7 spread of the focus point. So in theory, this one with the lenses a long way apart should give me a crisper focus point. But I think it's not that practical. And I can't see that 0.2 is going to cause me a major problem. And what I'm now going to do is to design a nozzle that fits this lens configuration. And I think I can do that and plug it onto the end of an empty lens tube with no lenses in it. This is the plan. We're going to mount two lenses, and I'm probably going to use an O-ring to separate the lenses. And I'm going to put them in one pocket at the bottom of a nozzle. And then we're going to push that nozzle onto the end of an empty lens tube. Now I have got a detailed drawing of this nozzle which I plan to make, and if it works, I see no reason why you guys, if you want to have a go at it yourself, shouldn't make one of these nozzles. Now if there's enough people interested, it may well be worth me getting a batch of these, maybe 50 or 60 of them, made on a CNC machine and making them available for you guys in a black anodized aluminium. What I'm using at the moment is a black Delrin material, and to be honest, it doesn't seem to be burning up or failing. If you're only going to use it for engraving, I can't see that there will be a problem.
Yesterday I made my new nozzle, and today we're going to see whether or not any of the predictions for it turn out to be true. So we're going to find out whether my foray into optical engineering proves me to be a genius or a muppet. So here I've got my empty lens tube and my new nozzle, which I notice has still got a little teeny weeny hair of swarf in it. And I shall just have to take that out. There we go. That's good. Now another important fact that I didn't mention about these two designs is that when you have the end of the nozzle, which is here, I've probably got to have about an 8 or 10 millimeter hole in here to let the beam through. When I put my nozzle here, and I know it looks quite large, but relatively speaking at 4 to 4.5 millimeters, it's a small hole for the debris to come back up if I'm pushing air through it. So I don't stand much chance of getting too much contamination of my lens with this approach, because first of all my lens is 15 millimeters back from the work,
as opposed to 8mm back from the work, and it's protected by a 4mm hole as opposed to maybe an 8 or 10mm hole. So many things commend this design approach as opposed to that design approach. There may be a small compromise that I've made with the, if you like, the intensity of the dot that I might be able to get from it, but hey, there's only one way to find out, and that's to test it. Lens, O-ring, lens, and a little plastic retaining cap on top, so that when I press this on, it holds the whole assembly tight. Now I've got an O-ring in here, which makes this a snug fit. Right, so making sure that I hold it upright, I'm just going to twist very slightly and push. Yep, that's a nice secure fit on there, and you can hear there's nothing rattling around. And I've got my piece of 4mm polyurethane pipe in here, which is a snuggish fit in that hole there. So we don't know exactly where the focus point is. We're going to have to find that out, but it's going to be hopefully about 5 or 6mm below that surface there, the end of the nozzle. So I think we're going to use our standard white card as our first test. This is one of the nice results at 254 dots per inch with newsprint. Now to do that, I managed at that point to get something which looked like a 0.1 dot with my little test pattern here. So if I put the same test patterns onto this sheet, I should be able to compare my new test patterns with my old test pattern. And we're somewhere in the 5 or 6mm. Let's start off at 5mm and see whether we think we have to go up or down from there. Now this is obviously a completely different lens configuration, but we'll start off with the same values that we had there, which is 200mm a second and 16% power, and we'll see what we get. As you can see from a distance, that's substantially darker than that one, so I'm suspecting it's going to be the wrong power and the wrong focus, and yeah, there's just too much power there. Yeah, the first thing is that looks very thick. Those dash lines look very, very thick, so the focus is obviously not correct. So we set it to 6mm now. Now bear in mind this is a short focus lens now, so it's going to be pretty sensitive to height. We'll leave the speed and the feed exactly the same because we're trying to find the focus point. And I would say that's getting thinner, so let's try 7mm. There we go. I'm sure you can see now I've got some crisp dots along the middle line, and it's getting a lot thinner along those dashes at the top. And I've also got some dots appearing on the bottom line. Well, we finally finished up with 6.5 there as our optimum focus point. We're beginning to get some small dots there, but I think I've still got far too much power there. When you compare the colour of that with what we had here, this is far too dark. In other words, the point that I keep making is that to get the smallest dots possible, we need less power, and with less power we're going to get less colour. The two things seem to be pointing to the fact that we're never going to be able to get to this magic 1000 dpi because we will lose the colour. They'll be invisible, and we'll see what we get with speed and power without compromising the focus. Well, we've got a selection of dots there that I think we must go and look at under the microscope. Okay, so here was our previous gold standard 0.1 dot. Pretty good. So let's move on to what we've just done. You can see they're in a different league. Those are pretty good, that first set, which 120mm a second at 12%. Now what I want you to do is to look at the dashes, the thickness and width of the dashes. As you can see, as we go to 11%, they somehow get thicker. And they get more scorching round the edge. 11%, they've got wider still when you compare them to the ones that you can just see at the bottom of the screen. And then we go down to 100mm a second and 10%. Now they're nice dots, but they have got a little bit of inconsistency along that middle row now. They're not quite as powerful. We haven't gained anything on the dot size, although these are definitely, looking at the gaps relative to the dots, the gaps are now slightly bigger than the dots, which means the dots are less than 0.1. Let's just work our way back down again. Dot gap about the same. Dot gap about the same. Now we're getting a bit confused. I mean, there are places there where the gaps are definitely a lot bigger than the dots. And I would say that that's about as good as we're damn well going to get. They look maybe 0.08, 0.075, possibly. Especially the dots towards that right hand end there. The gaps are definitely bigger than the dots. And when the gaps are the same as the dots, it's 0.1. When the gaps are bigger than the dots, the dot, well, we're going to have to estimate that dot at 0.075 to 0.8, 0.08. That has defined our new standard. 120 millimeters a second, 12% power, and 6.5 millimeters away from the job. Now we'll go and do some pictures, should we, and see what we can get. Okay, now I have decided to move away from my pretty mundane Tiger, because nice as it is, I think we're moving beyond its ability to show us good detail. So what I've done, I've managed to find this fantastic picture, which is basically a Photoshop collage, which has been designed as a tattoo. It's an arm tattoo. Now, like most tattoos, if you look at them carefully, there's all sorts of very subtle shading in them, which you don't get in photographs. Now, as I said, this has been purposely constructed as a collage from Photoshop. It's got all sorts of amazing detail in here. This is an inkjet print. Pretty amazing, the detail on here. I mean, look particularly at this point here. Let's just zoom in on one particular area that I want you to look at. And that's this clock. And it says on here, West London. And you can see all the little marks around the outside, the minute marks. Look at the detail on the octopus eye and his suckers. It's difficult to say whether they're ladies or not, or whether they're something like just fancy, like almost chess pieces. In the faintest way possible, in the background, look, there's a sort of map of the world. I've got to credit the guy that did this, because obviously it's a fantastic piece of artwork. I was particularly interested in this piece of artwork, as I said, because of the amazing detail that it's got in it. There's attempt number one. Okay, so it is a sepia version, because obviously I can't get black on with burning. We have got West, we have got London, and we have got all this very fine detail around here of the minutes. We've also got the octopus eye in great detail. And we've got all those columns in the background there. So this is, to be honest, an amazing replication of that original picture. And that's using Jarvis 254 dots per inch with my super duper 1.5 inch lens. So then we move on a little bit and we managed to get that. Now that's even more sepia, getting closer to the original. And here it's even clearer. But again, the octopus eye is really very, very clear. There's no smearing or smudging in this picture at all. I'm just absolutely blown away by the amount of detail that we've managed to capture. We've even managed to capture an even crisper image of the map in the background. Very, very faint. I suppose in real terms it is a sensible 0.1, absolutely 0.1 dot. And I've been able to get a really super crisp 254 dot per inch image out of the machine. Do I need to go to 1000 dots per inch when I can do it at a quarter of that resolution? What's the benefit? I certainly don't appear to be able to get any sharper than that. Now, as I said, I'm pretty confident that I shall get a physical Thunder Laser lens, high resolution lens. And what we've got here are some fairly demanding tests that we can run head to head to see just what it can do. This last picture with the Atkins dithering took 51 minutes to produce, but it's virtually a full-size A4 picture. Now, why you'd want to do that in 51 minutes as opposed to this much better coloured rendition in about 2 minutes or less on an inkjet printer, it's difficult to say. Obviously this is card, but we may be able to do the same thing on glass, which you obviously can't put through an inkjet printer. So that's something for a future session now, and that is to test this lens on glass, on perspex. Now I know that it won't work on stainless steel coated with molybdenum, because you have to put so much heat into the molybdenum to get it to bond onto the stainless steel, and there is just not that amount of heat here. We're very delicately plucking at the surface with just the point of our laser beam to try and produce the merest amount of burning. So the finer we can get the beam, the finer we can get the point, the less energy we put in and the more scorching we can do. That's been the aim of this exercise. We've got to go the opposite way to do engraving with stainless steel, but we certainly will be able to succeed with acrylic, and we may be able to succeed with glass, and that's a whole area that I haven't really explored, but we'll see just how good we can get. I'm very confident we'll be able to do this on anodized aluminium, but I just don't have any left to play with. I feel moderately smug because I've succeeded in doing something that I've never attempted before. I may well have got it totally wrong. Those of you that may be optical engineers might want to tell me that there is a much better way of achieving the same result. So, until the next time, thanks very much for your attention.